Hello and welcome to this presentation. My name is Magnus Malmström and I'm a PhD student at the Automatic Control Department of Linköping University. Today I will present the paper on the validity of using the delta method for calculating the uncertainty of predictions from an overparameterized model. I have written this paper together with my supervisors Isak Skog, Daniel Axel and Fredrik Gustafsson. So the main question is, what kind of algorithm are we working with? So in normal settings, if you have some image that you want to classify or an image you want to predict what's happening in the scene, you put a camera image to a classification algorithms which give out the decision. But this is not really what you would like to have. You would like to have some uncertainty. How certain are you that the thing that you're classifying the object is or the things you predict will happen in the future are true? So hence we presented a way to, instead of just have the decision, you have some uncertainty in the decision. So you have some bars. How certain are we that it was that car that we classified or that the car will turn right in the next corner? But then comes a problem. So usually if you're working with neural networks or any black box models, you usually use them too flexible. So maybe like in this case, you have this like a red extra part of the network, which is not really useful. So the model is overparameterized. So the question is then, how do you handle this? And how does this affect the uncertainty in the prediction? So that is what we want to investigate in this paper. So the agenda of this talk is as follows. I will start by motivating why it's important to know the uncertainty in the predictions of your models. Then and also why it's important to know how to handle overparameterization and how that affects the predicted uncertainty. Then we'll present the delta method, which is our method to quantify the uncertainty predictions for these models. Then we'll talk a bit about overparameterizations and different overparameterizations we have identified. And then I will summarize the findings of the paper in the end. So, why is the knowledge of the uncertainty important? So, in many applications nowadays, neural network or black box models are part of it. For example, in self-driving vehicles, if you want to classify some images, for example, here you have a bear, which we are classifying from camera trap images, or if you want to predict some economics, or try to detect tumors in images, in medical images. And it's important to know when to trust the predictions or how much you should trust the predictions from these models. Also, if you have multiple measurements of the same thing, you would like to fuse them to get one prediction in it all. So this example we have on the car, we have 5 cameras. Then we want to fuse the predictions for all these 5 cameras and maybe a LiDAR as well. And to be able to fuse the predictions, if you're using black box models such as neural networks, it's important to know the uncertainty in the predictions. And also, if you know the uncertainty, you can also use that to detect out of distribution samples and other serial attacks, which is also a crucial part for safety critical applications. So why is it important to study overparameterizations? So when you're using a data-driven black box models to model something, then to make sure that you get good accuracy and that your prediction is good, you often have too flexible model to make sure to be able to capture the dynamic of the things you try to model. And this is no problem since the parameters themselves doesn't have any meaning. The problem comes, however, how does this overparameterization or these extra parameters affect uncertainty in the predictions? And this is especially important if your way to quantify the uncertainty depends on the uncertainty in the parameters. And the delta method depends just on that. How uncertain are the parameters? And this is what will then result in how uncertain are your predictions. So what you're doing is you do linear approximations around the parameters your network has converged to. So in the training, you train this loss function Vn, given some training data, and you find this theta hat. And around this theta hat, you can model the distribution of the parameters as a Gaussian, with the mean given by the parameters you found and the variance given by the curvature of the loss function. And for neural networks, this is sometimes referred to Laplacian approximation of the Bayesian neural network. So we're not really interested in uncertainty in the parameters, but rather the uncertainty in the predictions. And we can move the uncertainty in the parameters to uncertainty in the predictions using a Taylor approximation. Hence, we approximate this nonlinear model with a linear one. And the idea of this delta method is that it can be used out of the box. So you can use your already trained model, then you can linearize it to find the uncertainty in parameters, and then you can linearize again to find the uncertainty in the prediction. And now it comes to overparameterizations. So in our work, we have distinguished two different kinds of overparameterizations. Either the added parameters does not add any flexibility to the models, then we call them redundant parameters of category 1. Or the parameters can add flexibility to the model, then we call them category 2. This maybe sounds a bit vague, so let's give an example. So if you consider the model f of x is equal to 1 plus 6x plus x squared, which can be described as a linear regression model, then overparameterization of category 1 is given, then you have this extra term in the regressors, which were summed in extra parameters, which is this x plus 1. Well, if you have a more flexible model, so a model of category 2, then you would have add this x cube, which results in a more flexible model. So the main results of this presentation and this paper is that uncertainty is larger or equal for an overparameterized models if you compare to the model with a minimal flexibility to be able to model the true underlying system. And here we call this minimal model the canonical model and denote it by the subscript C. So there's basically, if we use the delta method to move uncertainty from the parameters to uncertainty to the predictions, you will always have larger or equal uncertainty if you have a too large model. And equality holds here when the redundant parameters are of category 1, and that is that they doesn't add any flexibility to the model. So these results we have also validated using simulation experiment. The data comes from the magic formula tire models, which describes how the normalization traction force depends on the wheel slip. The canonical model here can be shown is given by neural networks with one hidden layer and two nodes in hidden layers. So hence we have constructed a regression functions which resembles these canonical model. So in this example, you can see that when we increase the number of basis functions or the number of regressors, so regress with this red one is the canonical one, and then you have the yellow, purple, and green. You can see that the uncertainty in the predictions increases as the flexibility of the model increases. So this is when we have an overparameterization of category 2. While if we have an overparameterization of category 1, you can see that the uncertainty is the same over the whole interval. We also try this when we have a nonlinear model. So in the previous example, there were linear regressor models. Here we have neural networks with increasing number of nodes, which were trained. And you can see the same phenomenon that the uncertainty increases as the model flexibility increases. So what is a summary of these presentations? So if you're using the delta method, which is an out-of-the-box method to include uncertainty predictions for your model, and if the model is overparameterized, we know that uncertainty is larger or equal to the uncertainty of a model with minimal representations if you use the same method to include uncertainty. And we have shown that the equality holds when the redundant parameters or when the extra parameters does not add any flexibility. Hence, we can conclude that the uncertainty, for an overparameterized models is not underestimated. Thank you for your attention. If you have further questions, you can either email me on my email address, or you can talk to me at the IFAC World Congress. There's also some information on my local homepage. Thank you.